So this is the fourth lecture for the power engineering module, and we are done with AC circuits. We will now start magnetic circuits. So yay. Before we start with magnetic circuits, I would just like to throw some electrodynamic formulas at you, and the reason is that these come straight from Maxwell's equations. There is nothing we can do about it. It's like trying to prove Ohm's law. This is fundamental. So the formulas are, this is the definition of magnetic flux. So there's nothing much to be concerned about this. This is the major formula that we'll be dealing with. What is this? If you have some path, closed path over which you are integrating the H vector, then that is same as the flux of the current vector through that. So this is like Ampere's law if you remember. These form the ground for all mechanical magnetic circuits, and this is the magnetic circuit that we'll always deal with. This is my favorite. Now take this equation and apply this to this path. Now first of all let me explain this magnetic circuit then. So the mean core length is LC. This is the average of all the possible core lengths that you could possibly have. So the core length is one whole path like this. The cross section is AC. There are n windings and the winding has some current I. We'll talk about lambda later. It's important. We'll talk about it. The air gap is important. It has some permeability mu naught. The core itself has some permeability mu. Then if we apply this along path, so I have taken the mean core length, right? So I'm assuming H to be constant along this. So H times L is simply the current through this surface. So the current through this surface is basically all these. So there are n windings, so Ni. HL is Ni, right? Now the equation 2 across one single cross section. What does that give? Well, that simply gives me that BA is phi. And now all you have to do is try to connect H and B and you will be done. If the material is linear, this is easy. So that's called a linear magnetic circuit. It is my favorite circuit. So we can define this Ni value, that integral of H dot dl over the path, as some MMFF. So why do I call it MMF? It will come to you in 2 minutes. But well, we are defined EMF as the electromotive force, right? So this is like the magnetomotive force, F. For a linear material, B is mu H. So now we start writing the formula. F is Ni and Ni was defined to be HL. Now HL can be related to B as BL over mu and B was phi over A. So now you have some MMF proportional to some flux. The constant of proportionality you could say is something called the reluctance. Now observe that this is strikingly similar to an electrical circuit. How, you ask? Well, the MMF is acting like a battery. This is acting like a battery and the flux is like the current that is flowing through the circuit. So the opposition provided to the flowing of that flux should hence be the parallel of resistance. So this should be something like the resistance. It's called the reluctance. So there are a lot of new opposition terms that will come in this module: reluctance, impedance, reactance. So this is called the reluctance. Just keep this in mind. So the air gap that I'd shown, it's actually usually deliberately built into the circuit. Why? Well, let's see. When you have an electric circuit, you need some path through which the current can flow, and that's why a wire is there, right? You provide the path through which the electric current can flow. So you need some path through which the magnetic flux can flow, and that path is provided by the magnetic material. But as with a wire, you can't have a potential drop across the wire because we simply write that the potential of across the whole wire is the same. Similarly, you can't have an MMF drop across a magnetic material because its mu is too high. It's like saying that the conductivity of the wire is too high. It cannot have a voltage drop. So we put a small air gap which acts like the reluctance. Now this is a bit different from an electrical circuit because you can't simply open the electrical circuit and then say that there is an air gap which is acting like the resistance. That's a bit weird because no current will flow. But here you can do that. A small air gap will act like a reluctance. It will allow the flux to flow through it. Now air gaps are linear in nature always. There is no approximation here, and that permeability is the vacuum permeability. It is 4 pi into 10 to the power minus 7. Now reluctance behave like resistances when you add them in series or parallels. You could use those formulas in these circuits, and a common assumption is to take that air gap area that we have introduced equal to the area of the core. Although this is only applicable for small air gaps because we are neglecting the fringing around those air gaps, right? Now we come to the lambda that I had talked about. That is called flux linkage. So this lambda. So the flux through the coil. So since there are n turns, the flux links n times. So the linkage is lambda equal to n phi. This is called the linked flux. As this flux changes through this circuit, as I changes, the whole H changes, which changes the B, which changes the flux, the which now creates some EMF. This is how EMF is produced. So the EMF produced is minus d lambda by dt. This is simple. This is Faraday's law, right? And the minus is Lenz's law. Now the ratio of lambda and I is called inductance. So you produce some linked flux and it is proportional to the current. This is how it is proportional to the current. So L is lambda over I. Now we know that lambda is n phi, so it is n phi over I. Now we remember that flux is like the current, right? So it is voltage over resistance. So it is mmf over reluctance. Now you see, you could simply write F as Ni, right? So you write F as Ni, you get N square over R. So this is an important result. What is that? The inductance is inversely proportional to the reluctance of the magnetic circuit. And if the inductance is constant in time, you could pull it out and you could write it as L di by dt. Now what if the magnetic material is not linear? And this is where things start getting a bit shady. See, for most materials, what happens is when you start increasing H beyond a certain point, you need to increase the H a lot to see a small increase in B. In simple words, what happens is you need to provide lot more current just to get a small increase in the flux, right? And in such cases, if you apply a sinusoidal EMF, the current that is now produced is no longer sinusoidal. So this is what happens. If this is what your flux looks like, so this is if so see what happens is, until now we have been talking about E equal to minus L di by dt, right? And since the reluctance of linear magnetic materials does not depend on anything, it is independent. If E was sinusoidal, so would I. It would simply look like an inductor, right? And we know that both of the current and voltage are sinusoidal across an inductor. But if you do this, if you start making the magnetic material non-linear, this is what the BH curve looks like. Then it has some hysteresis. It looks weird. So if you start applying a sinusoidal EMF, this is what the current would look like. Now notice this is the y-axis is actually like this here, right? So this is how time is increasing and this is what the current is looking like. So it's inverted. Don't get confused that there are many current values at the same t. It's inverted. Now in such a scenario, you can see that there is some area of the BH curve, right? And so it will start consuming energy to let the flux pass through it. Now the energy lost to hysteresis per unit volume per cycle is actually equivalent to the area of the BH curve. And in an electric circuit, this current that is now, because in the electric circuit point of view, you will see some weirdly behaving current. You can approximate it to a sinusoid. So how do you approximate it? So this is basically we are trying to transform the magnetic circuit into some electrical component. We are trying. So the approximate sinusoidal current is chosen to have the same RMS value as the actual current, because then we would have the same RMS. So we have been crying about RMS for some while now. But how do you determine that phase shift from the V? So you determine it such that the power loss is the same. So Vi cos phi is same. But Vi cos phi can now be calculated because you know that the area of the BH curve is the power loss per unit cycle per unit volume. So the power loss actually has two components. One is hysteresis and one is eddy current. What is eddy current? You are changing the flux. So actually if the magnetic material is like iron, it will allow eddy currents to build up inside it. And those eddy currents will face some resistance in the iron. They will dissipate some current. They will dissipate some energy, sorry. So they will also draw energy. So actually what happens is, some people think of this as drawing a fatter BH curve. So what I mean here is that this BH curve that you are seeing, if you apply this at 60 Hertz, which means if I'm traversing this one loop one time 60 times in a second, right? So what happens is the hysteresis is so powerful that this curve starts getting fatter. Now Some people say that no, this is the BH curve that is being traced and eddy current is a separate thing. Some people say no, the current the whole this graph gets fatter, the BH curve gets fatter, it increases in the I dimensions, and the extra area that you get because of that, that is the power lost in eddy current. So those are the two ways of thinking about eddy currents. But these actually can be very much minimized, and you could do this by cutting the core into very small pieces. So now, and then putting it back together after applying some insulating varnish in between. So now there aren't as many loops possible for the current to flow, the eddy current to flow, not the winding. Now, once the flux is determined, we can form a current phasor, right? So basically, we try to find an equivalent electric circuit that can model this magnetic circuit. And the best such model that you will find is actually an inductor and a resistor in parallel. So why is that? This is a very common question. Why do you place them in parallel? The reason is that the eddy currents change as flux changes, right? It doesn't depend on what current is flowing through. It basically depends on whatever flux is going through the magnetic circuit. The flux changes, the iron feels that it should flow some eddy currents. The flux is the derivative of the flux is the EMF. So basically, the flux is proportional to the EMF. The flux is always sinusoidal in nature since the EMF applies is sinusoidal in nature. Hence, the eddy current loss should technically be proportional to V square, right? It should not depend on the current that is needed to magnetize this whole thing. There should be some separate current which should allow for the loss that is happening in this whole eddy current phenomena, and we have seen that this loss is proportional to V square. So hence, a loss that is proportional to V square is V square by R. So add the resistance in parallel. Basically, the current that is magnetizing is not the reason for the loss. The current that is reason for the loss of the eddy current is the eddy current. It is not the magnetizing current. What if you have more than one windings? So then you will have to take the flux because of one winding through the other, and then the flux through itself also. So then you will have, like, suppose you have a circuit like this, there are two windings and then there are air gaps. So the flux because of this through this, because of this through this, because of this through itself, because of this through itself. So you have four values. So the mutual inductance, which means the ratio of flux through here and the current through here, there are two such combinations, right? So there will be two mutual inductances, and it turns out they are both the same. You can even derive a formula for that. That's called the Newman formula, and this is actually an outcome of generalized machine theory. That's out of the scope, way out of the scope. But if assume that the core was linear, we could model such a circuit by saying that it has some self-inductance L1, this has some self-inductance L2, and there is some mutual inductance M. Now, see, suppose there was no EMF across it, there was some EMF across this. That would set up some flux, and that flux would be changing, which would produce some EMF across this coil, which inspires one to try to apply a voltage on one coil and receive voltage of different magnitude on the other side. And here is where we come to the fact that now we can see that maybe we can step up or step down the voltage in an AC circuit, and hence the result would be a transformer. This is the end of video 4. Thank you.